Welcome to lesson 2.4b, angles at a projectile. Now, before we even get into filling all of this out, I want to look at this little picture here. And what this is outlining is that parabolic motion of what's happening when something is coming at an angle. Now we see two things happening with an angle. We have a velocity that goes in the x direction, marked in blue, and we've got a velocity in the green in the y direction. Notice that the y is constantly changing, right? And we see an acceleration down. It is always moving down. We see that change is always in that negative direction. But also notice that the velocity in the x direction, the blue, never changes. So when we take a look at that, what's happening in the x direction? We've got no acceleration. And because we've got no acceleration, we've got uniform motion, and so we'll use the formula of v is equal to d over t every time we're dealing with things in the x direction. But in the y direction, we have an acceleration due to gravity. And so that means the acceleration is negative 9.81 meters per second squared. And we'll be using, it is angled, so we have an initial velocity that will not be zero, like we had with the horizontal. So this will equal something that is not zero. Right? The formulas we'll use here are going to be like d is equal to vit plus 1/2 at squared, or a is equal to delta v over t, etc. But there is one thing that is constant in both the x and the y direction, and that is the time. Time, whatever's happening in the x direction, is also happening in the y. We take a look, both these things in the blue and the green are happening at the same time, leaving us as a result of the red. Okay, so we should note that as well. Also notice that when we're right at the top, the velocity in the y direction was 0. Sometimes you'll get questions that say maximum height, and maximum height means where the velocity is equal to 0 in the y direction. Right? So what's different about angled projectiles by comparison? Well, the key thing is that we separate the initial velocity into horizontal and vertical initial velocities. So let's take a look at an example here. An object is kicked with a velocity of 10 meters per second, 37 degrees to the horizontal, and we're calculating the distance the object will be in the air before hitting the ground. And so this is coming like this. Our angle is 37 degrees, and we're starting off at 10 meters per second. We want to find this distance, and that's really all we got. But if we separate into the x and y component, we can separate this 10 meters per second into x and y initial velocities. Given that's 37, that would be 10 sine 37. And so on the y, that's going to have an initial velocity of 6.01 meters per second. So let's put that in there. Got an initial velocity of 6.01 meters per second. And here this is 10 cos 37. Will get us the velocity. Notice I'm not saying initial velocity, just the velocity, and the x direction, and that's going to be 8.0 meters per second. Really, this is a two-digit question. I should say 6.0 and 8.0. But we want to find out the distance here. We know that the acceleration is equal to negative 9.81 meters per second squared. We know that the overall displacement is 0. And so what that means here is, because the acceleration is constant, we can also make the assumption that that final velocity is negative 6.01 meters per second. So finding the time in the air, A is equal to delta V over T, or T is equal to that change in velocity over A. That change in velocity is negative 12.02 over an acceleration of negative 9.81. That gets you a time of 1.223 seconds. Time is the one thing that can go between the x and the y, so we can say that the time is equal to 1.223 seconds. Now, the distance is easy, or displacement is easy. Just multiplying the two should get you 9.77 meters. Okay, let's take a look at another example here. And in example number 2, what we've got is an A and B, and the first part is just figuring out how long the time is in the air, because we can't use that same sort of trick. It's got a displacement of negative 25 meters, and this object is being thrown and coming down. And so finding this becomes a little bit difficult, but we will separate everything into the x and y component. We've got that 18.0 meters per second at an angle of 53 degrees. So finding the x and the y component, that's 18 cos 53, and this is 18 sine 53. So if we take a look here at 18 cos 53, 18, that gets you an initial velocity, or a velocity of 10.8326, but we'll just go 10.8 meters per second in the x direction. In the y direction, that is 18 sine 53, and that's going to be 14.37 blah 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 meters per second. So we're breaking this apart into the x and the y components again, but just to find the time in the air, all we really know is the velocity in the x direction as being 10.8 meters per second, and the initial velocity here is 14.37 meters per second. But we also know the acceleration is negative 9.81 meters per second squared. We also know the displacement is negative 25.0 meters, and we want to find time. So using d is equal to VIT plus 1/2 AT squared leads us with a little bit of a problem, because our displacement is negative 25, VI is being 14.37, T plus 1/2 negative 9.81 T squared. Notice we've got a quadratic equation here. So how do we solve this? Well, we can solve that graphically. And because we're only worried about really going to 2 or 3 digits, really 2 because of the angle, what we're going to do is, in our calculators, just pressing y equals, you're going to put the two sides of that equation in here, right? So side 1 was 25, negative 25, and so we put that in for y1. y2 had all of this, and so that's what we're putting in. Don't forget your negative. And our window settings are going to also need to be adjusted here. We're going to need our y minimum to be 30, because we had a y is equal to negative 25. For it to show, we need to also have that in range here. So when we graph it, there's our y is equal to negative 25. Here's that quadratic. And we've got two intersects. Second function, trace, and we're going to find where these two lines intersect. moving close to this curve. Now you'll notice that there's two here, one with a positive, one with a negative, but we're really only concerned about that positive time, which will be over here. First curve, second curve. Guess. Notice it's 4.156 seconds. And that's your time, 4.156 seconds. But to 2 digits, we would just call that a time of 4.2 seconds. Now the part B, which we'll do in green here, how far from the base does the object land? Well, that time we know is 4.156 seconds. D is equal to T times V. And so that's going to be taking the 10.8 and multiplying it by 4.156. That should get you a 44.9 or 45 meter range. Okay, again, those steps, just to recall, to find the time, we enter in this side of the equation for y1, we enter this side of the equation for y2, and we find where they intersect in order to find the time. Helps us get through that quadratic. Okay, we've got one more. I would like you to try this one. Pause the video. Give this one a try here, and you should wind up with an answer of 57.2. If you do get 57.2, you know you've done it right. But pause the video, give this a try, and we'll go through the answer. Okay, so welcome back. First thing we do here is we separate things into our components so that we can put them into the y and x and fill in our information. With the y direction, we know the initial velocity, acceleration, displacement. We're looking for time. Generating this equation, you should find a time of 2.70 seconds. Time being the thing that happens in both the x and y, that is the same, means that you're going to now take that to 21.2 meters per second multiplied by the 2.70, and that gets you, in fact, 57.2 meters. Okay, I hope that helped. If you have any questions, let me know.